In the last class, we discussed about the potential due to a dipole, and we found that potential at every point on the equatorial plane of a dipole is zero. So the potential due to a dipole at a point depends upon the angular position of the point also. Now, another point is, if you have a continuous charge distribution, then potential due to such a continuous charge distribution is found by dividing that charge distribution into small elements. Suppose an element of volume delta V, and since the charge density, if it is rho, so this gives the charge on the volume element. So dividing that charge distribution into small elements and calculate the potential due to each such volume element of the charge at a point, and you have to sum up for all such elements. Here summation means integration. So by integrating over the entire charge distribution, you will get the total potential for a continuous charge distribution. So that is the method how we calculate the potential due to a continuous charge distribution. Similarly, we studied that for the electric field, due to the charge distributed on a spherical shell, acts as if the whole charge is concentrated at the center. So the potential at any point for outside the sphere is given by 4 pi epsilon naught some q by r, where r is the distance of the point from the center of the sphere. Now, on the surface of the sphere, so on the surface of the sphere, let us suppose the radius of the sphere is, say, some capital R is given by this. At every point on the sphere, this will be the potential. So here we assume this is in the case of a point outside the sphere, where this radius, this distance of the point is greater than this, and at every point on the sphere, this will be the formula. And you know, inside the sphere, at every point the field is zero, but the potential is not zero. In the case of a charged hollow sphere, the potential is same at every point on the sphere, and also same at every point inside the sphere, but the electric field is zero. Electric field zero doesn't mean that the potential should be zero. Okay, so therefore you need not do any extra work to move the charge inside the shell from point to point. Therefore, the potential remains same at every point inside the hollow charged sphere. Now we will talk about equipotential surfaces. Equipotential surfaces. See, what are equipotential surfaces means? If the potential is same at every point on the surface, then we call it as equipotential surface. In the case of a point charge, the potential is generally given by this formula, like this. So if r is the distance of the point on the surface, for every point at the same distance, potential will be same. Therefore, you can imagine in the case of a point charge, the potential is same, say at some distance r, means the locus of all such points will appear like a concentric sphere with the charge at the center. So you can imagine such concentric spheres of different radii. So all such concentric spheres are nothing but equipotential surfaces to this point charge. Okay. Another important point is the field direction will be always perpendicular to the equipotential surface. If it is not so, there will be a component in the direction of the equipotential surface. So if there is a component of electric field, then there must be potential difference between 2 points on the equipotential surface. Hence, you have to do work in moving the charge on the equipotential surface. So this is against the definition of equipotential surface. Since potential is same at every point on the surface, you need not require any work to move a charge on such surfaces. But if the electric field has a component in the direction of the equipotential surface, then work is to be done. Then we cannot call it as equipotential surface. Therefore, we can conclude that the direction of electric field will be perpendicular at every point to the equipotential surface. So that is the equipotential surface. Then we will discuss about relation between electric field and potential. Very important topic. So consider two equipotential surfaces. Two surfaces, say some A and B. So let us say this is surface A, this is surface B. The potential of A is say some V. The potential of B is say some V plus delta V. See, this plus delta V doesn't mean that it is having more potential than this. There is only a change in the potential of B when compared with A. So let us suppose the separation between the surfaces is say some delta L, perpendicular distance between the surfaces. Now consider a point P here on the surface B, and you know that normal drawn to the surfaces, if that gives the direction of the electric field. So the potential difference between the surfaces is equal to work done in moving a unit positive charge from the surface B to A. So that gives the potential difference. Therefore, if E bar modulus, that is the magnitude of the electric field at this point P, then to move the test charge from, that is positive charge, in the direction opposite to this electric field from surface P to surface A along the normal direction. So this into delta A, because that is the distance moved, and we have multiplied this with unit charge. So that is not being shown here. So EQ is the force in terms of electric field strength. You know, the force is given by EQ. Force into distance gives the work done. So here the Q is unit charge. That's why I have not shown that to 1. So magnitude of this electric field strength multiplied with the distance between the surfaces B and A. So this is equal to potential of A minus potential of B. So that gives the potential difference. So that is nothing but V plus V minus V plus delta V. So that is equal to minus delta V. So therefore, the electric field strength is given by minus delta V by delta L. So this is a very important relation. The electric field strength is defined as negative gradient of potential. Electric field strength is defined as negative gradient of potential. That means we can discuss two important points from that relation. Number one is the electric field has the direction along which the potential decreases at the maximum rate. So the direction of the electric field will be along the direction in which the potential decreases at maximum rate. And another point is, we can also say that the decrease in potential is steepest. The direction along which the potential decrease in potential is steepest. So that direction we call it as the direction of the electric field. Now another point is the magnitude of electric field strength is equal to the magnitude of the change in potential per unit displacement along the normal direction of the equipotential surface at that point. So we can also define the magnitude of electric field strength is equal to the change in potential per unit displacement along the normal direction at the point on the equipotential surface. So these two are the important points we can discuss from the particular equation. So this is a very important 2 marks question, relation between electric field strength and electric potential. So when we discuss about capacitors also, we come across this relation. So this relation is very important to derive the expression for the capacitor. Okay. So next topic we'll discuss is the potential energy of a charge system. So that means electrostatic potential energy of a system of charges. See, already this topic was briefly discussed earlier. Now, potential energy of a system of charges means, suppose you brought a charge Q1 from somewhere to a point where there is no other electric field, no work is to be done. Is it not? So, if you bring, suppose a charge Q1 from somewhere to a point where there is no electric field, you need not do any work. So, the potential of at the point where you brought the charge is 0. Now, suppose you bring another charge, say some Q2, without disturbing the position of Q1. Then you are bringing this Q2 into the field of Q1. So therefore the potential energy is given by that is U is equal to potential energy is given by 1 by 4 pi epsilon naught. It is the, suppose that point is at a distance of say R12 from this Q1, then this gives the potential due to this charge at a point which is at a distance of R12. So this is Q1. So here is say Q2 R12, and now we know potential of unit charge is, that is work done per unit charge is this. So when you multiply with the charge Q2, then that is the potential energy. So that is nothing but what we did is, potential means work done per unit charge. Therefore total work done for a charge, to bring a charge Q is given by this formula. And one more point, you should know that V is equal to work done per unit charge. That is what we derived in the earlier equations. So joule per coulomb is the unit of the potential difference or potential. Okay. And you know, for potential this is equal to volt. Okay, we will discuss about it while we discuss current electricity. Okay. Then here, how do you derive this? Means the potential due to Q1 is this one at a point at a distance R12 where Q2 was brought. So the total work done is this. Suppose you bring another charge, say some Q3, to this position. So here it is R13, and from this it is R23. Then in such case, Now this Q3 is in the field of Q1 and also in the field of Q2. So therefore the potential due to V1 is our total potential V1 plus V2, we can write. Then multiplied with the charge Q3 gives the potential energy due to work done against the electric field created by Q1 and Q2. So that is V1 Q3 plus V2 Q3. So that can be written as 1 by 4 pi epsilon naught common, and here Q1 Q3 by R13 plus Q2 Q3 by R23. In addition to that, you have this Q1 Q2. So therefore, total energy, that is total work done, actually is given by, so this plus this. So you have to add these two. So that is 1 by 4 pi epsilon naught is common. Then what is there? So Q1 Q2 by R12 plus Q1 3 by R13, sorry, Q1 Q3 by R13 and Q2 Q3 by R23. So that is the total potential energy of the charge system. So for a charge configuration, the total potential energy depends the state of the charge system, but is independent of how the configuration of the state is achieved. So how you brought this Q2 and Q3 is immaterial, because we know electrical forces are conservative forces and potential energy is depends only on the configuration of the charge system, but is independent of how that configuration was brought about. Okay, so in this way we calculate the potential energy of a system of charges. Now let us consider how to calculate the potential energy in an external field. Similarly, we can do it for dipole also, but we will go for potential energy in an external field. So here what we talked is there is no external field here. We talked about the field created by the charge. Into that field you brought the other charges. But how to calculate the potential energy if the charges are brought into an external field? Potential energy of system of charges in an external field. Suppose a charge Q is brought into an external field, say of a field strength E, then you know the force acting on it is EQ. So that is the force. Now here we are not bothered about how this electric field is created, what is the charge that is creating it. So in an electric field you brought a charge Q, and for bringing the charge you have to do work done. So therefore that potential energy, as usual, force multiplied with the distance. How much distance you have to do. So you can put it something like this, dot, so R1. So where R1 is the position of that charge from an arbitrary origin. So you have to imagine an origin from which the point you are considering is angular position vector R1. So in this way you can calculate the potential energy of a charge. Suppose you are bringing a number of charges into an electric field, then how do you calculate that potential energy? Let us do that. See here, this can be also written as Q into potential of the electric field at the position of R. So at this position, let us suppose R, but if the potential of the electric field is say some V, then multiply gives the potential due to a charge kept in an electric field at an arbitrary position R bar from the origin. Now, if you consider a system of charges, so let us suppose you brought the charge Q1 where to a point where the potential is say VR. So, the potential at the point where you brought the charge Q1 is say some V of R1, and you brought another charge Q2 to some other point where the potential is say V of R2. Therefore, the total this is the work done to bring the charge Q1 and this is the work done to bring the charge Q2. In addition, these Q1 Q2 are also separated by some distance. So therefore, the total potential energy will be like this: Q1 V of R1 plus Q2 V of R2 plus you assembled the two charges. So 4 pi epsilon naught Q1 Q2 by separation between them. It's like this. So this is the total potential energy of system of charges when they are brought into an external electric field. So this is how we have to calculate. Now let us see what is the potential energy of a dipole in case of an electric field. So let us see how to find out. So potential energy of a dipole in an external electric field. Suppose you have here a dipole. This is say minus Q, this is say plus Q, and say this is the direction of the electric field. So we already used this concept for deriving the potential, that is the potential or what happens to the dipole kept in a uniform electric field. So the torque formula you derive. Now suppose this is this such that let us imagine the direction of the electric field is making an angle theta, and this is the direction of the dipole moment. Okay, and you know the distance, the length of the dipole, as you know earlier we said some 2a is the length of the dipole. So in such case what happens? This electric field will try to rotate the dipole in its direction. So let us assume an equal opposite torque is applied on the dipole to bring it from some angular position theta naught to say some theta, and we already derived that torque acting on the dipole is given by Pe cos sin theta. This is what we derived. So the magnitude of the torque is given by Pe sin theta, and using right hand thumb rule you can find out the direction of the torque or the moment of the couple. Now the work done, total work done in rotating the dipole from a position of theta naught to theta by the external torque, because we have to counteract this torque exerted by this electric field by using external torque, such that without any angular acceleration, it was you have to imagine that no additional acceleration is given, and so with the small angular speed it is rotated from position theta naught to theta without angular acceleration. then the total work done is given by integral of, so tau into d theta. That is the formula for work done by the torque. So from position theta naught to theta. But already we derived this formula for the torque acting on a dipole. So this can be written as like this. Integral of dipole moment P, electric friction P, sin theta d theta from theta naught to theta. And you know, integral of sin theta is cos minus cos theta. So therefore, you can write this one like this. That is minus P cos theta, or between the limits, or we can write like this. Theta naught theta, like this. So this can be written as PE into cos theta naught, because upper limit you have to substitute first, then lower limit, then we can write it like this, because there is a minus sign here, cos theta. This is how we can write. Now the initial position, generally we consider the potential whenever we calculate potential energy or potential. We consider the charge to be at a point where the potential is 0. So we assume arbitrarily that for a position theta naught is equal to pi by 2, the potential is 0. Then in such case, this work done is given by minus PE cos theta, or we can write P bar dot E bar. So this is the formula for work done in on a dipole kept in a uniform electric field. Okay. So when the dipole is rotated from, say, some initial position, that initial position we have taken, that it is perpendicular to the field direction. So from that, it rotated. When you rotate it by an angle theta, so that is the work done. So we can also assume that, suppose if the dipole is parallel to the field direction, theta will be 0 degrees. In that case, the potential energy formula can be written as PE 1 minus cos theta. And suppose if you rotate the dipole from the direction of the electric field by an angle of 180 degrees, pi radians, in such case, this potential work done, this work done is PE 1 minus 1, because cos 180 is minus 1, then we will get 2. So that is equal to, this is the maximum value. So if theta is 180 degrees, okay. So and so here, if theta is equal to 0 degrees, then W is equal to PE into 1 minus cos theta. The initial position is 0 degrees. Then it is P into 1 minus cos theta. If it is rotated opposite to the direction of the electric field, then the potential energy of the work done, which is told as potential energy of the electric potential energy of the dipole, that is equal to 2 times PE. Okay, so this is about the work done or potential energy of a dipole kept in an external electric field.